about gases. One, they have high amounts of energy. Okay, so high energy. Okay, the molecules, gas molecules have high energy. That's why they're moving so fast, okay? And we know energy and heat are two words that are synonymous, okay? If you're adding heat to something, you're adding energy to it. So they have high energy, and we could say kinetic, if we're trying to be specific, which I think it's good here. High amounts of kinetic energy. Here's another question. Are these molecules in the gas phase really interacting with one another very much, you think, if they're moving so fast? They are not, okay? So we have no, I'm gonna say intermolecular interactions. Intermolecular means interactions between molecules, okay? So the analogy I like to give here is these are like cars on an interstate, okay? They're not sitting and chatting, they're zooming past one another, okay? You can't talk to someone that you're driving down the interstate with from car to car. Obviously we have phones and stuff, but that's not what I'm talking about. No intermolecular interactions. They're not interacting with one another, all right? Now let's move over to the second picture. B is the middle one here. Is this, obviously we've knocked out gases. So is this a solid or a liquid in the middle? Yes, in the chat, I'm hearing liquid, liquid, liquid. That's true, this is a liquid. So let's define the same kind of stuff. Let's define the same kind of stuff here. The amount of energy and the kind of, or the level of interactions between the molecules compared to gases and solids. Liquids are kind of gonna be middle of the line. So these have some, I'm gonna abbreviate KE, kinetic energy. Okay, some kinetic energy, not as much as gases, but more than solids. Because how do we know that? The molecules are fluid. Okay, liquids, we know the molecules are fluid. They can move past one another. So if some kinetic energy, let's talk about it from the angle of attractive forces between the molecules. Do you think the molecules are interacting a lot or a little? What do y'all think? Jenna says some. So obviously they're not moving as fast, but they definitely look more crowded here. So we could say for sure there's got to be more attractive forces between the molecules. So we'll say, I'm going to use the word some again. Some intermolecular interactions. All right, so they're kind of in the middle. And then obviously this last one is the solid state. And you can see, if we zoom in on this, these red spheres, by the way, obviously represent molecules or atoms. And we can see here in the solid state, the molecules are very arranged, okay? That's why we say they're the most ordered and gases are the least ordered. Gases have a lot of disorder, entropy. You guys remember that from chapter 7. So they're very arranged and structured, which means, are they moving around? They're held in place, right? So do they have a lot of energy? No. So they have very little kinetic energy. It doesn't mean they have no kinetic energy. Oftentimes, molecules in solids are described as vibrating. So they do have energy, it's just that they're not flying around the way gas molecules are. So very little kinetic energy. They are held in place. They are ordered. And what about their intermolecular interactions? Do you think there's a lot of attractive forces between molecules or atoms in a solid compared to gases and liquids? If those molecules are being held in place, there's got to be attractive forces there. Yeah, a lot. So they have a lot of intermolecular interactions. Okay, a lot of attractive forces in between those molecules that are holding them in place. So I want you to definitely see a trend here. As you go from gas to solid, we are losing energy. Remember, same word as energy, you could say heat as well. And as you go from gas to solid, so that's one thing. The second thing is you are increasing the strength of intermolecular interactions. Okay, we're losing energy. They're moving slower and slower and slower until they're held in place, but the kind of intermolecular interactions are increasing. Okay, there's more interactions between the molecules of solids. So another way that we can kind of visualize this arrow thing that I just drew is with this figure on the right side of the slide. So I'm going to slide over here. This diagram is in your textbook as well, and it's just showing you and demonstrating phase changes, okay, changes between solid, liquid, gas, the common names that go with those, and then what's happening with heat, what's happening with energy. Are we absorbing energy in each case, or are we releasing energy? It's going to sound like a lot like enthalpy, and this is exactly, you know, we could define a positive or a negative delta H with each of these processes, okay? We can also define a positive or a negative delta S with each of these processes. But obviously we have gas at the top, solid at the bottom. So let's just start here with solid. If we follow this first arrow up, we know as we go from a solid to a liquid, that's called melting. As you go from a liquid to a gas, you're vaporizing, boiling also is another word. And in both ways, as you travel up this figure, you are absorbing heat. You're absorbing energy, okay? Because gases have more energy than liquids, and they have way more energy than solids. So it makes sense they have to absorb heat. You have to absorb heat to melt ice. You have to absorb heat to boil a liquid or for that liquid to vaporize. Okay, so these are high energy, high in heat, high in energy. But vice versa, as we go down, I'll do this with a blue arrow since the text is in blue. As we condensate something, go from gas back to liquid, as you freeze something, you must be giving off heat so that those molecules can come closer and closer together and then interact as a solid in place. So those processes, the middleman there is a liquid. You're going from a gas to a liquid, liquid to solid. However, on the other side of the figure over here, if we draw an arrow straight down, there are processes that take us directly between gases and solids. We're less familiar with these processes, but they are there. We call this deposition. If you are taking gas, making it directly, skipping the liquid state directly to a solid, that's deposition. You're releasing a ton of heat here. You guys might be more familiar with solid to gas. Okay, we call that sublimation. All right, solid to gas. Now, anybody think of an example of sublimation? There's a substance that's relatively common that sublimates. Anybody know what I'm talking about? It's called dry ice. Anybody familiar with dry ice? Okay, if you're traveling on a long trip, sometimes people, or like large 18-wheelers, they'll be packed with dry ice because it doesn't melt. It stays cold for a long time, but it just gives off a vapor. So look up a YouTube video on dry ice if you're not sure what I'm talking about. It doesn't melt like regular ice. It just sublimates. So that's an example there. So keep in mind with these processes, if we had to go in and put in delta H, if we're absorbing heat overall, that is a positive delta H, right? If you're releasing heat overall, these processes where heat is released is a negative delta H overall, okay? So if I gave you a process like melting or freezing or condensating or sublimation, and I ask you, what's the sign of delta H? Okay, you could tell me, right? Equally, you could also tell me the sign of delta S, okay? If you're going from ordered to disordered, okay, these processes in red, this is going to be a positive delta S. You're increasing disorder. And if you're going from gas back to a solid, these are going to be a negative delta S, okay? So keep that in mind as well. Any questions so far? Okay, so speaking of intermolecular forces, again, these are forces that occur between molecules. or atoms. I put 2 S's on that, by the way. Or atoms. Between, not within a molecule, but between two neighboring molecules. There's different types of intermolecular forces. And so we're going to define 3 of them and look at, compare them to one another and see how they affect substances, gases, liquids, and solids. The first kind that we're going to talk about is called a dipole interaction. Sometimes for short, we just call them dipole. Okay, dipole interaction, dipole moments, dipole interactions, all the same thing. The second one we're going to talk about is known as London dispersion forces. They have a nickname. They're also known as, I'll zoom out in a second, Van der Waals forces, due to the scientists that recognize them or define them. So London dispersion, also known as van der Waals, and that's interchange. You'll probably hear me use those terms interchangeably. The third one is known as hydrogen bonding. Okay, so these are the 3 kinds of intermolecular forces that we're going to define, and we're going to see how they affect substances and what kind of substances have them. Okay, so the first one, let's talk about dipole interactions. We're just going to fill in a few blanks first, and then we're going to look at examples of how they affect molecules. So this first blank over here is molecules that are polar. Or for example, have a dipole. If you are a polar molecule, you have a dipole. You guys remember us drawing dipoles in these things on molecules that are polar overall or have polar bonds or lone pairs and they're not symmetrical. Molecules that are polar or have a dipole, they will experience dipole interactions. Okay. Dipole interactions are the strongest force for polar molecules, ones that can't hydrogen bond, and we'll get to that, but molecules that are just polar. And so what happens here is the positive pole of one molecule is attracted to the negative pole of another. And that's exactly, hold on, I'll let you fill in those blanks. The positive pole of one molecule is attracted to the negative pole of another molecule, a neighboring molecule. And that's exactly what you see in this first picture up here with the red and blue ovals. So if we have polar molecules, and we can assign a positive, semi-positive portion and a semi-negative portion with the little delta signs you see. Between neighboring molecules, the negative side lines up with the positive side of another one, and they orient themselves this way. Here you just see 4 molecules, 4 individual molecules. Imagine this with like 1,000 molecules though. Imagine it with 1,000,000 molecules. Okay, they would all orient themselves. It actually brings a lot of order to the substance. They line up in this way, and they kind of create a network of arranged molecules. And so there's if we had to draw little dashes here between these, here's your little dipoles, the attractions at play. Okay, they're invisible to us, but there's attractions that are ordering and arranging those molecules, and those are dipoles. Now, the next blank is that they are stronger than London dispersion forces, but they are weaker than hydrogen bonding. So they are kind of your middle class strength force. Stronger than London dispersion forces, but weaker than hydrogen bonding. So I want to look at a real example. Why do we even care about dipole interactions? Well, I'm going to show you 2 molecules down here. One that's polar, one that's non-polar. And we're going to look at a difference on a very real property. Okay, boiling points and melting points are properties that we can measure for any substance. Okay, you guys remember when we talked about like specific heat? Specific heat will affect like boiling points and melting points as well. But dipole interactions will affect those. So look at these molecules down here. Which one would you say is polar? Which one is non-polar? Let's talk about butane. Butane is C4H10. Carbons and hydrogens only. Do you think this molecule is polar or non-polar? The chat, people are saying non-polar. Okay. Non-polar. Good. It is non-polar. And in fact, if you look at the kind of sphere model here, the carbon-hydrogen bonds are never polar. Carbon-carbon bonds are never polar. So this is nonpolar. On the flip side, we have acetone. Anybody ever dealt with fingernail polish remover, which is basically acetone? It kind of dries your skin out. This is a polar molecule, and we can see that because you have the partial negative right here, and you have the partial positive right here. So you have a polar bond between carbon and oxygen. All of these other bonds, the hydrogen-carbon bonds that I'm drawing lines over, these are nonpolar bonds, but you do have that one polar bond between carbon and oxygen. So this makes it a polar molecule overall. Because of that, I want to look at, one, we have their molecular weight listed. Look at that. Their molecular weights are identical. So they're essentially the same size molecule. So it's not the weight or the mass of the molecule that matters here. But right beneath that piece of information, what do you think BP stands for? And it's a temperature. That is the boiling point of these substances. Look at those numbers. For the nonpolar molecule, it's negative 0.5 degrees Celsius. Is that high or low? I'll tell you this, 21 degrees Celsius is room temperature. So negative 0.5 degrees Celsius is really low. What does that tell you? Butane boils with like no heat at all, less than room temperature. It'll boil. Okay, so essentially at room temperature, it's definitely a gas. All right. Now, what about acetone? Acetone boils at 56.2 degrees Celsius. That is really, really hot. So it takes a lot of heat. So the difference here is over 50 degrees Celsius difference in their boiling points, all because of these one little bonds, these polar bonds between the carbon and the oxygen on acetone. That's a huge difference. 50 degrees Celsius is a lot. Why does it take so, and they weigh the same, okay? They have pretty much all the same atoms except for an oxygen here is the difference. But the difference here is because molecules of acetone can have dipole interactions. If you had a whole bucket full of acetone molecules, okay, one dipole interaction between, say, two molecules, if we just had two molecules, that one little dipole interaction is not going to mean much. But if you have thousands and millions of dipole interactions, that's going to, you're affecting a property of this molecule in a large way because those add up. The individual dipole interactions add up and they become very strong overall. So I just wanted to illustrate that looking at the difference between the boiling points here. Any questions on how dipole interactions work? Okay, let's move on to the next one. Van der Waals forces, AKA London dispersion forces. First blank here is that they occur in all molecules. Every single molecule, even the polar ones, experience van der Waals forces, okay? It's just that in polar molecules, van der Waals are not the strongest. The dipole interactions are the strongest. They are dominant, meaning London dispersion forces, van der Waals, they're the strongest force in molecules that are nonpolar. So they're dominant in nonpolar molecules. They overall are the weakest intermolecular force. And now, again, we're not saying they don't matter because if you have millions of molecules all experiencing London dispersion, they will add up and they will affect the properties like boiling points and melting points of substances, but they are the weakest. These are caused by interactions between momentary dipoles. So that sounds confusing. Wait, I thought dipoles are dipoles. Well, these are caused by momentary dipoles. And how is a momentary dipole different from a dipole? Okay, up here, we're talking about permanent. I didn't spell that right. Permanent, pretend that says permanent. Permanent dipoles. Down here, how is a momentary dipole different? Let's draw a picture. If we have two atoms, let's just say hydrogen. Here's my nuclei. Here's the electron cloud. And we know in a hydrogen molecule, H2, we have a bond between these hydrogen atoms, right? There's the bond. So I'm drawing the picture up here, and we have electrons, okay, we often draw them as sitting nicely, nice and still, right between the hydrogen atoms. But do electrons sit still? About as still as probably my 2-year-old, okay? They don't sit still. They're moving constantly. Electrons are moving constantly. So at any one point given time, I'm going to actually take those electrons off. At any one point given time, the electrons may both be over here. They may both be over here. They could be right in the middle. Essentially, they're moving all over the place. This is honestly what's happening. They're just moving all over the place. So if we were to take a camera and take a snapshot, the electrons may not be in the middle. They may be on one side or the other. And because of that, let's say our electrons, I'm going to do them as red spheres. Let's say they're both over here in the molecule. Let's say our two electrons are over here. And let's just say they happen to be next to a neighboring molecule. Let's see, I don't know what this is going to copy and what it's not. Okay, let's say they're next to a neighboring molecule that, you know what, they have a momentary dipole and the electrons, oops, sorry, I want to draw them on the other side, happen to be on the other side as well. Now there's a momentary dipole where for just a moment, this is the semi-negative side, and on this molecule, the neighboring one, this is the semi-positives for just a moment. But there is a dipole. It's very temporary and then it's gone. But for that moment, there's an interaction here, okay? That's what a momentary dipole is. And I know that seems very, very small and as though it would not matter, but they do matter and they do add up. So this next blank, 2, is that larger atoms tend to have more electrons, or they do have more electrons, and therefore they tend to have more fluctuation. And therefore, they tend to experience more London dispersion interactions. So I've drawn example with hydrogen atoms. Now imagine this with, I don't know, like cesium. Cesium has tons and tons of protons and therefore tons and tons of electrons. And if all those electrons are moving, and instead of just saying a difference of 2 electrons here, what if we're dealing with 100 electrons? Then you can see how the shift would be larger, okay? So because of that, molecules with as well larger surface areas will have more London dispersion interactions. So we're going to look at an example of this with the 2 figures I have down here. How surface area impacts London dispersion forces and then how that affects melting and boiling points. So atoms with a larger atomic number, more protons, therefore more electrons, they have larger London dispersion forces, more London dispersion forces. And then molecules with larger surface area. How does surface area deal or affect anything? I'm going to erase a little bit so that you can see. Well, let's look at pentane here and 2,2-dimethylpropane. What I notice is if you look up the molar mass of these things, it's the same. We have the same number of carbons and hydrogens, okay, in these structures. 5 carbons on each side, and 12 hydrogens in each structure, okay? Both of these have 5 carbons and 12 hydrogens. So they're the same mass, essentially. But you can see one, pentane is longer, okay? It's elongated. It's kind of more of a elongated, all the carbons are just in one chain. So therefore, this one has more surface area. And 2,2-dimethylpropane is kind of wadded up into a ball. It looks more spherical and less elongated, right? And if we were to draw the Lewis structure, you would see that it's just a different way that the carbons are attached together. So because of that, this one has less surface area. Now look at their boiling points. 1, pentane boils at 36 degrees Celsius. 2,2-dimethylpropane boils at 9.5 degrees Celsius. Okay, so that's almost a difference of 20 degrees Celsius difference. Why is there a difference here if they have the exact same kind of atoms involved in same number? Well, obviously, if it's got more surface area, this one has more London dispersion forces or interactions. And that is what makes, we got to input more heat or more energy to boil that substance, all right? So it has a higher boiling point. We got to add more heat to it to break all those London dispersion forces and cause the molecules to go into the gas phase. It takes less energy, less heat to break apart all those London dispersion forces and cause these 2,2-dimethylpropane molecules to enter the gas phase, okay? Questions on how, essentially the more interactions you have, the higher the boiling point. The fewer interactions you have, the lower the boiling point. Vice versa, the stronger the interaction, that you have, if you have molecules that can experience dipole interactions versus London dispersion forces or van der Waals, that will have a higher boiling point as well. That substance would. Okay, let's talk about the last type of intermolecular interaction. Can I say that again? The more interactions, the more intermolecular forces. By the way, I'm just going to call these IMFs, intermolecular forces. We're going to call these IMFs. So the more IMFs that a substance has, the higher its boiling point. The fewer IMFs, or the weaker the IMF, intermolecular forces, the lower the boiling point. And melting point, same trend. The lower the boiling point, the lower the melting point. The more forces, the higher the boiling point, melting point. The less forces at play, the lower. And you have to look at what kind. If you're comparing a molecule that it can experience dipole interactions versus a molecule that it can experience van der Waals only, then that will affect the level of their boiling points and melting points as well. Dipole interactions means higher melting points and boiling points. Any other questions? Okay, last one, hydrogen bonding. This one actually pertains to, we owe it our greatest and deepest respect, okay? Hydrogen bonding is the reason that water is a liquid at livable temperatures compared to a gas, okay? If we did not have hydrogen bonding, we would have to do a whole lot of work to have liquid water. But we have the perfect temperature zone, and water experiences hydrogen bonding, water molecules do, and that's why we have liquid water on Earth. Thank the Lord. So first of all, because of that, I'm going to say they're the king of all intermolecular forces. And basically, because they mean we have liquid water, they're responsible for all life on Earth. We could not survive without water. I once knew someone, they said they never drink water. They're like, I drink juice. I just drink juice. I don't ever drink water. I drink Cokes and I drink juice. I'm like, you don't drink water? When's the last time you had a glass of water? And they're like, well, I don't know. I couldn't tell you. Please drink water. Don't do that to your body, okay? You need water every day. Do you know how much water you need every day? I'm gonna drink some water right now. Ew, is water ew? Or are you saying that just drinking juice is ew, Brennan? Yeah, 7 to 8 glasses. You need like 64 ounces of water. Okay, gallon challenge. All right. Strongest intermolecular force, responsible for life on Earth. Let me show you how. Yes, thank you, Brennan. I knew that's what you're talking about. Let me show you how important they are. Here's a picture of, y'all know what this is, the molecular structure of DNA. Anywhere you see a red dotted line, that is a hydrogen bond. So this is DNA, and I know you see a lot of carbons and hydrogens and atoms portrayed onto this helical structure, because we know DNA is a helix. It's actually a double helix, but you just see one helix here. And any of these red dotted lines, okay, these things, these are all hydrogen bonds. So what does that mean? That means literally our DNA is held together by hydrogen bonds, okay? Thank you, hydrogen bonds, for holding my DNA together. Another way that they're important is they hold proteins together. Do you know how many proteins are in your body, roughly? Yeah, it's funny. I start talking about water, everybody gets thirsty at the same time. Roughly 60,000 proteins in your body. Isn't that amazing? Proteins are held together by hydrogen bonds as well. And proteins are essentially the workforce of your body. Anything that gets done, I'm biased towards proteins. I did all my graduate studies on proteins. Anything that gets done is because of proteins, okay? They do all the housework. They do all the chores, all right, essentially. Here's a picture of water molecules. And you can see when you put water molecules in a room together, they're interacting. All these little dotted lines, these are all hydrogen bonds. So this is a network of water molecules all held together by hydrogen bonds, okay? So do you believe me now that they're important? Okay. So what exactly is a hydrogen bond? We're going to use these pictures up here to show you an example of one hydrogen bond. But first, let's define it. What they are is it occurs between the lone pair on any oxygen, nitrogen, or fluorine atom. These three specifically, and these three only. The lone pair on an oxygen, a nitrogen, or a fluorine, and a positively polarized hydrogen. That is also bonded to another oxygen, nitrogen, fluorine. I know this is a very technical and specific definition, so we have a little bit to unpack here. But what is positively polarized? That essentially means any hydrogen that has one of these on it. Any hydrogen that's involved in a polar bond with an oxygen, a nitrogen, or fluorine. Okay, so what that looks like is you've got to number one, I'm gonna write them right down here. Number one, you've got to have a lone pair, okay, on an oxygen, a nitrogen, or we know fluorine has 3 lone pairs. There's the picture of it. Number two, you've got to have a hydrogen bonded to an oxygen, hydrogen bonded to a nitrogen, a hydrogen bonded to a fluorine. And all of these hydrogens are positively polarized. What that means is all 3 of these bonds are polar bonds. Those are the 2 requirements. The lone pair on the oxygen, nitrogen, fluorine, and then a hydrogen that's positively polarized because it's bonded to another oxygen, nitrogen, and fluorine. Okay. So that's the definition. Now let's unpack a little bit. Let's look at some hydrogen bonds. So I'm gonna slide over here. If I need to go back, just tell me. Right here, we see 2 water molecules. Okay, these are the electron clouds. So kind of imagine the water molecule without those electron clouds. But the electron clouds are important because we have to have the lone pair in those electron clouds to have the hydrogen bond. So, whoops, what am I doing? Okay. So this is 2 water molecules, and right here, this is the hydrogen bond. So this is just showing you kind of the ball and stick model. And then this right up here above it is the exact same thing, but we have the atoms written in as H's and O's. So here's 1 water molecule. That's the first water molecule. And then here's the second one over here. And you see the hydrogen bond in between those 2 as the red dotted line. So here's the oxygen. I'm going to point out this oxygen right here. You can see it's got a semi-negative charge on it. And you see the hydrogen on the neighboring water molecule has that semi, I'm going to trace over, it has the semi-plus. So this is the positively polarized hydrogen, and there's our kind of semi-negatively charged oxygen. We know oxygens are very electronegative, so are nitrogens and fluorines. So they're going to attract the electrons to themselves. So when 2 water molecules get in close proximity, there's that bond right there. Now, what we call this hydrogen, we give this hydrogen a name, and we give this oxygen a name. So this is going to be what we call the donor. It is essentially donating some electron charge to this other oxygen on the neighboring water molecule. And we call this oxygen the acceptor. It's happy to accept more negative charge because it's electronegative and they have high affinity for electrons. So we've got the hydrogen, the positively polarized hydrogen is always the donor, and the oxygen, or the lone pair essentially on any oxygen, nitrogen, fluorine is always going to be the acceptor. So if I give you 2 molecules and ask you, can they hydrogen bond? I would definitely want you to show me, be able to draw that out, and then label acceptors and donors, okay? Or be able to count how many acceptors or donors. So the lone pairs, guess what? This lone pair is another acceptor. So we have 2 acceptors on this oxygen, and then this hydrogen is a donor. Guess what? This hydrogen could also interact if we had another water molecule over here. If we had an oxygen with 2 hydrogens, okay, there could be another hydrogen bond right there. And we could label this. This could now be our donor. And these lone pairs on the oxygen are, guess what, acceptors. Oops. So on and so forth. So that's an example with water molecules. Let's look at another example. 2 molecules of ammonia, NH3. We've studied this guy a lot. NH3. NH3 meets all the requirements, both requirements here, because we have a lone pair right here on this nitrogen. Is that the acceptor or the donor? Is the lone pair the acceptor or the donor? What do y'all think? Yeah, always the acceptor. The lone pair is always the acceptor. And this hydrogen right here, the one that's positively polarized, this is the donor. And that red dotted line is the hydrogen bond, okay? And notice that this hydrogen is bonded to another nitrogen, all right? And that's why it is positively polarized, because this bond right here is polar. Now, you guys are like, you're talking a whole lot about electronegativity, and I forgot that stuff. Well, we can't forget it, which is why, where did I put it? Where did I put it? Right there. We're going to need that chart, okay? Don't forget your old friend, electronegativity. I'm going to put that chart on the resources page for you for exam 3. And if you're wondering, well, how do you know these are polar bonds? Let's look at the electronegativity of hydrogen, and then these 3 elements are the ones that are important when it comes to hydrogen bonding. Hydrogen has an electronegativity of 2.1. Okay, remember, nitrogen here is 3.0, so what's the difference between these two? 0.9. That is polar. Remember, anything from 0.5 to above 1 was polar. Almost, I think, above 2. Okay, oxygen is even more electronegative, 3.5. So the difference between hydrogen and oxygen was 1.4. So that's polar as well. And then fluorine is 4.0. So the difference between 2.1 and 4.0, that's even the largest difference. That's so polar, it's almost basically ionic. 2.9, right? Or 1.9, 1.9. Okay. So just a reminder on how electronegativity and electronegativity differences work. So just real quick before we move on, you can have molecules that can only have one requirement or the other, okay? So essentially you can have molecules that can hydrogen bond with themselves. Okay, we just looked at 2 examples. Water, for example, water and ammonia are 2 molecules because they both, in one individual molecule, if I draw water, HOH, it has both a donor and an acceptor. Okay, these hydrogens can be donors, and the lone pairs on the oxygen, these are the acceptors. So molecules that can hydrogen bond with themselves, they have both requirements. They have a donor and acceptor in their molecule. But some molecules can still hydrogen bond, they just can't hydrogen bond with themselves. Some molecules only have one or the other. Maybe they have an acceptor, but they don't have a donor. Maybe they have a donor, but they don't have an acceptor. So let's think of examples of that. So molecules that maybe they can hydrogen bond with, for example, water, but not themselves. It's because they have only one or the other. What I mean by that is they have either an acceptor or a donor, but they don't have both. Can you zoom back in on the NH3 picture? Up above, on the slide above, Allison?
Yes, please. Okay, I'm good. Thank you.
You're welcome. So can anybody think of an example of a molecule that can hydrogen bond with water, but maybe couldn't hydrogen bond with itself? Challenge question. Maybe it has like a positively polarized hydrogen, but it doesn't have an oxygen, nitrogen, and fluorine. What about something like HCl? You got to ask yourself, is this hydrogen positively polarized? Well, let's go look at that electronegativity chart. I'm going to scroll down. I'll be right back. There's chlorine. The value is 3.0, and hydrogen we know is 2.1. So just like nitrogen is 3.0, chlorine is 3.0. So yeah, that is a polar bond. The difference is 0.9. So this means that the hydrogen is positively polarized here. But we don't have a donor, or sorry, that is a donor. We don't have an acceptor. We don't have a lone pair on an oxygen, nitrogen, or fluorine. So two molecules of HCl, if we had another one right here, they cannot hydrogen bond. These lone pairs on the chlorine, they do not allow for hydrogen bonding. Okay, so we have a donor, it's just that, but if we had a water molecule, so what if we have a water molecule instead? It can hydrogen bond with a water molecule because you have the oxygen, which has the lone pairs that we need, and we have these positively polarized hydrogens. We could get a hydrogen bond. I'm going to draw a blue dotted line here between the hydrogen HCl and between the water molecule, okay? Because here is our donor, and now we have an available acceptor. Okay, so these are just some examples. You could think of many more examples, but I just wanted to differentiate these two. You have molecules that can hydrogen bond with themselves in pure form, but they have to have both requirements, a donor and acceptor. If you have one or the other, then you can hydrogen bond, just not with yourself. You could hydrogen bond with water. Any questions there? Okay, so now we're going to put this to practice. We've got a little bit of time left. First off, as a review, what characteristic must a compound have to experience the following intermolecular forces? Take a second, just brief words, just like a phrase here, one or two words. What kind of molecule do they have to be to experience London dispersion forces, dipole, and hydrogen bonding? Hydrogen bonding might be more than a little bit of a phrase. You got to have two things there. Anybody want to tell me or remind me for London dispersion what the requirement is? Got to be nonpolar. This is kind of a trick question because all molecules experience London dispersion. But yes, they have a temporary dipole, and essentially they're the strongest for nonpolar, but essentially there are no requirements. Any molecule has London dispersion, okay? So they're all molecules. I'm just going to say all molecules have them. No requirements there. But they are made up of a momentary dipole, temporary dipole, and they're the strongest force for nonpolar molecules. Okay, what about dipole forces? You have to be what? Polar. That's right. Thank you, Allison. You have to be a polar molecule to have a dipole. And hydrogen bonding, what are the requirements there? There's two. The first one, put it in your own words if you want. First one is you have to have a positively polarized hydrogen. Thank you, Jenna. The second one is that you have to have a what? Yep, lone pair on oxygen, nitrogen, or fluorine. You at least have to have one or the other to hydrogen bond with another molecule, but to hydrogen bond with yourself, you have to have both. So I want you to, we're probably going to do like A, B, we'll try to do all three, but D, E, and F, I have poll questions for those because I want you to take a minute and write those out and put your answers in on the poll. So let's look at A. We're going to identify. The question here is what's the, you could just say dominant intermolecular force in each of the following substances. So what do we have to do? We have to draw out the Lewis structure here. They are following us all the way through this semester, Lewis structures. So nitrogen, we know, is a triple bond to another nitrogen. So is this a polar molecule? Is it non-polar? What do y'all think? Can a hydrogen bond with itself? Allison says it's nonpolar, okay? None of these are polar bonds. There's 0 electronegativity difference between a nitrogen-nitrogen bond. So this is definitely nonpolar. So the strongest force here is what? London dispersion. London dispersion. Yep, I'm going to abbreviate LD. Van der Waals, London dispersion, same thing. That's the strongest force for molecules of nitrogen. What about HCN? Let's draw the Lewis structure for that. HCN. So we should have a carbon. It's got to have 4 bonds on it. Nitrogen has to have 3 bonds. Hydrogen has 1 bond. So how would you draw that out?
Would it be carbon triple bonded to nitrogen?
Yes, Aaliyah.
And with the lone pair.
It says 1 bind to hydrogen. And yes, lone pair on that nitrogen. Boom, there it is. So what do y'all think about this molecule? By the way, I have the electronegativity chart right here. You probably heard me say, and you maybe should remember, that carbon-hydrogen bonds are never polar. So this bond right here, this is nonpolar. But carbon-nitrogen, we have a carbon-nitrogen bond. Okay, these two, the difference there is 0.5, and that is polar. So we have a semi-negative side and we have a semi-positive side. And we can draw a dipole in on this molecule. Boom, that direction. So because it's polar, there's no symmetry here. So the strongest force at play would be what?
Dipole?
Yep. Dipole-dipole interactions. Okay. So that's B. We'll do C really quick, and then I'm going to let y'all do D, E, and F. So C, we have CCl4. So that should just be a carbon with 4 chlorines bonded. And those chlorines all get 3 lone pairs each. What do y'all think about this molecule, CCl4? Allison says nonpolar. Why? I'm pretty sure that the carbon-chlorine bond, the difference is 0.5, so that's a polar bond, but why is the molecule nonpolar? Symmetry. That's right. There are actually 2 planes of symmetry. 1 plane there, 1 plane there. You could fold that molecule over either way. So this is, because it's got symmetry, this is nonpolar. Okay, don't forget about the symmetry aspect. So therefore, the strongest intermolecular force, because it's nonpolar, is what?
London dispersion?
That's right, London dispersion. Okay, so if I gave you a molecule and said, what's the strongest force at play here? You could do this kind of thinking and tell me. So I want you to take just a minute. I'm going to launch this poll. Go ahead and do the same thing we just did, but for D, E, and F. I'm going to pull the poll up. Why is my poll not here? I had polls for these. I'm not seeing it. Okay, well, do it on your own anyways. Draw them out and then write what is the dominant intermolecular force. You have NH3, CH3Cl, CH3COOH. That's very frustrating. Oh, wait. Maybe it's right here. There it is. Launch pole. Okay. So you can put your answers in for each of these once you finish them. If anybody was paying attention a couple slides ago, NH3 should be real easy. Okay, about halfway there. $20 of 27, almost there, almost 80%. Give it another 30 seconds or so. And then we'll go over these, and this will be all we do for today. All right, end poll. We're pretty much there. Share results. Okay, here are the results. Here's what you guys said. For NH3, I'm going to scroll down. We got a whole blank slide right here. For NH3, most people said hydrogen bonding. We know the nitrogen-hydrogen bond is polar. We defined that earlier. It's a difference of 0.5. So because these are polar bonds, all of these hydrogens are positively polarized. You could draw that in. And so guess what? We can label this. In the same molecule, you have the acceptor, lone pair on a nitrogen, and all three of these are donors. So this can hydrogen bond. That's the strongest force here. Yes, they could dipole as well. You could have dipole moments. Yes, this molecule experiences London dispersion, but the strongest force is hydrogen bonding. It's not that it doesn't experience dipole or doesn't experience London dispersion. It's just the strongest force is hydrogen bonding. Okay, so most people got that one. Okay, CH3Cl.
I didn't get that. Could you try again?
Do y'all hear my Siri?
Yes.
Siri, shut up. All right, CH3Cl. Okay, what do we think about this? Well, we know carbon-hydrogen bonds are not polar. So none of those three carbon-hydrogen bonds are polar, but what about a CCl bond? CCl difference is 0.5. So this bond right here is polar. We can draw a dipole in. We could actually draw the partial positive on the carbon and the partial negative on the chlorine. Look at all those lone pairs. You can draw a dipole in. There's no symmetry here. So most people said that the dominant force for this is hydrogen bonding. But we don't have a positively polarized hydrogen. Okay, none of those hydrogens are positively polarized because the carbon-hydrogen bond is nonpolar. And we don't have a lone pair on an oxygen, nitrogen, or fluorine. So we don't have any of the requirements for hydrogen bonding here. So it cannot hydrogen bond, but it is a polar molecule. So the strongest force at play here is dipole-dipole. What am I writing? Dipole, dipole. Questions on that one? That one was split. Oh, wait, I was looking at results 3. Most people did pick dipole, dipole for 2. For result number 3, most people picked hydrogen bonding. So that is CH3COOH. What does this molecule look like? CH3 group. And we have another carbon. And what is OOH? Well, what that looks like, it cannot look like this. Why? Why can it not look like that? Because this carbon only has 2 bonds. So we can't have that. So we could have a double bond to oxygen here. Then we can have that OH group right there. And then that satisfies all of our bond requirements. Now, what's the strongest force at play? Let's just start with the hydrogen bonding. I noticed that we have an oxygen. Well, we definitely have lone pairs on oxygens, okay? But we have this hydrogen right here. Remember, none of these hydrogens are positively polarized. Why? Because they're bonded to carbon. So those are not polar bonds. But this hydrogen over here is bonded to oxygen. And that is definitely polar. Okay, difference of 3.5 and 2.1. That's a difference of 1.4. So that's a positively polarized hydrogen. And this is the semi-negative portion. You could draw it right there as well. And so we have both requirements for hydrogen bonding. We have the acceptors. In fact, let's point out all the acceptors. Any lone pair could participate in hydrogen bonding. So how many acceptors are on this thing? A lot. Any lone pair is an acceptor. We got 4 acceptors here. And we also have 1 donor. Okay, so your numbers of acceptors and donors do not have to be even. You just have to have both, okay? So we can definitely hydrogen bond here. That's going to be the strongest force at play. Yeah, on the ammonia, you had 3 donors, 1 acceptor. Over here, on this one, you have 4 acceptors, 1 donor. Doesn't matter the number as long as you have both. So I'm going to close this poll. And essentially, that's it for today. I did have another practice slide, so we'll just have to get to it another day. But on that next slide, practicing which species can hydrogen bond in its pure form versus which one could hydrogen bond just with a water molecule. That's the difference of asking yourself which molecule has both a donor and an acceptor, or which one has just one. Maybe it just has a donor, or maybe it just has an acceptor. If it only has one, then it can hydrogen bond with water, but it cannot hydrogen bond with itself. If it has both, it can hydrogen bond with itself. And then maybe some of those don't have either. Okay, so that'd be good practice. But I want to launch this one more poll. I haven't done this in a while, but I actually really like this question. So just answer this for me. How much of this did you comprehend clearly today? Okay. So again, if you are in the 50% or less category, we need to maybe assess why that is. Are you struggling with Lewis structures? Are you struggling with the electronegativity stuff? Drawing in dipoles? Because this is a layered question here. There's a lot of material that you need to have comprehended well. I'll go ahead and end the poll. There's a lot of material that you need to have comprehended well to actually answer these kinds of questions. So if you are not good with drawing Lewis structures, you're like, I don't even know where to begin to draw a Lewis structure. That's going to be a problem on the exam for the chapter 8 stuff. If you're like, I don't even know how to define if a bond is polar or not, you need to go back. This is all chapter 4. You need to reach out to me. Let me know. We could talk about it on a Zoom, okay? But do not wait for the exam because it's 1 week from today. That seems very, very soon, and it is. So most people said they got nearly 75% and or more. So that's good. But a lot of people said only 50% or so. So if that's you, those 10 people, please reach out to me or go review chapter 4 stuff on Lewis structures and polarity, and let me know how you're doing after that. So, all right. Well, I will send an email with some updates either tomorrow or Thursday. Remember, there's going to be a bonus